We're ready to begin our discussion of Lie groups and Lie algebras. And prior to that, we're discussing briefly the concept of different types of tensor notation, including Dirac notation. Dirac notation, like for a three-dimensional space, which we never really see, would be written in the following kind of way. If we think of normally the unit vectors I, j, and k as unit orthonormal set of three vectors, then we could write the vector that looks like this with a vertical bar and a right bracket with a 1 inside, a 2 inside, and a 3 inside to represent those three vectors. We can talk then about orthonormality as the what is called the bra vertical bar ket, bra ket, meaning the as Dirac referred to them, the bracket, or the bra vector times the ket vector, I and j gives us a delta ij. This is actually what we would call a dual space. Anytime we take a scalar or inner product of one vector with another vector, that is a mapping of the vectors onto the real numbers. And that mapping can be shown for any given vector here to be a vector space within itself. So as I fix a vector here and take all inner products with another vector, that mapping is in itself a vector space, which is what is called the dual space. So now we can write any vector A and express it as A times A1 times 1 plus A2 times 2 plus A3 times 3, where A1 is equal to AX, and so forth. It is critical that we both be able to talk about an abstract operator and an abstract vector independent of any particular basis that we want to use. And that is true of any particular indexing of those vectors. For example, a particular indexing with respect to a basis might be the expression of L as an Lij, which would be a matrix of numbers, and A as AI, which is a set of real numbers or perhaps complex numbers. Well, this is accomplished, the change between the abstract L and A and the expression in terms of real or complex numbers is accomplished in terms of using something called the decomposition of unity. The decomposition of unity is the vector is an expression of 1 decomposed by products of the form back-to-back bra and ket vectors, with an I in each one, where I is to be summed or integrated, and if it's a continuous range we'd put an integral here, over all of the range of the vectors that we have as a basis for the space. With the Einstein summation convention, we can even say 1 is equal to this. Now the implication here is this first vector projects onto the system and takes its scalar product, takes that number and uses it as the component multiplying the ket vector. So the bra does a projection onto one side of the operator or the vector, and then that is used as a component. Let's look at some examples here. Certainly the vector A, an abstract vector, is 1 times A, which is I times I, the completeness relation, or as it's sometimes called, or the decomposition of unity. This relationship here times A, which is equal to, and now you'll notice that we have the vector A projected onto each of the basis elements, which is something which we call A sub I. We're not here distinguishing between yet contravariant and covariant. And then times AI. There is a summation here, which means that we are writing here the vector A as A1 times the vector 1 plus A2 times the vector 2 plus A3 times the vector 3, and that is exactly the formula that we have right up here that we have reproduced by this methodology. More precisely, we can take a vector L and put a 1 on each side. Now we have to be careful here so that we put i's over here and j's over here. We can't put the same index because these are summed. We see with an operator we have 1 on each side of the operator L. So we have a summation over i's here, summation over j's here. And now we have the object L in between a vector I and a vector J. This is a bra vector and a ket vector. This object right here we define to be the object Lij. And that object is now multiplied by the ket vector I and the bra vector J in this exact pattern here with a summation sign. These are the components of the tensor, the second rank tensor, in this particular basis. Now, in all of this, we write Lij is equal to ILJ, and AI is I times L. If we looked at the dual of this vector, we could write this as a complex conjugate or a dual to that. We will not be needing a metric with what we will be doing, but if it were required, it would take the following form. We would write the completeness relationship 1 as a sum or an integral over alpha and beta of alpha, g alpha beta, which is the metric, beta. Thus, an inner product would take the form A times B as two abstract vectors, A alpha, G alpha beta, B beta, or G alpha beta with a summation and integration convention of Einstein times this object, which is A alpha, B beta, assuming no complex conjugation. We won't be actually doing this in our Hilbert space. Our Hilbert space will have a very simple metric of just being 1. But there are times when we do have a metric in the Hilbert space that will arise in the Lorentz group where there's a sign difference. And that sign can be traced back to the sign between c squared t squared minus x squared minus y squared minus z squared. One good place to review the Dirac notation is to go back and look at a book like Massao's book on quantum mechanics, where he goes through the mathematical foundation of unitary operators and Hermitian forms and completely discusses the Dirac notation. Of course, you can always go to the original book by Dirac, which I think has gone now through 4 editions, and is a good place to also learn this, although it's a little bit more difficult than looking at Massao's book. Lie groups and Lie algebras in a nutshell, so to speak. And we believe that the fastest way to learn this material is to have a brief introduction and then to plunge right in and practice analyzing various groups and algebras. Then we'll do the abstract theory. That doesn't mean we won't do some of the abstract theory first, but we'll do the minimum amount that'll help us get by as we go through 6 or 7 of the different fundamental Lie algebras and Lie groups. Lie groups consist of a continuous infinity of elements that are not connected, that are connected with the identity element 1 by a transformation, e to the lambda times L. As lambda goes from 0, where we have e to the 0, obviously, and this is the identity, up to larger and larger values of L, the group is spanning greater and greater distance in some directions of a transformation away from the identity. Lambda dot L is here a vector in a linear vector space spanned by a basis vector set, Li. Just like in 3 dimensions, we would have a 1, 2, and a 3. However, these Li's are not regular vectors. They're objects which have an antisymmetric product defined. And this antisymmetric product, LiLj, is equal to Cijk Lk with a summation over the k. This bracket of Li and Lj is always equal to the negative of Lj Li. These objects right here are constants called the structure constants of the Lie algebra, and they tell us everything we really need to know about this algebra. Everything is really buried in that particular set of constants. Thus, e to the lambda times L is the element of the Lie group that corresponds 1-to-1 with lambda dot L, an element of the corresponding Lie algebra. So there's a 1-to-1 correspondence between the elements of a Lie algebra and the elements of a Lie group. But the elements of a Lie algebra can all be built from a particular basis, a certain set of L's. And we have that set of L's in the form lambda 1 times L1 plus lambda 2 L2 plus lambda 3 L3. There's a basis for that linear vector space that is generally finite. And therefore we can study the entire algebra just by studying those few objects that do the infinitesimal transformations that are foundational to that algebra. Now don't worry if this seems kind of difficult. We'll restate and re-explain each of these concepts many, many times. We'll use the abbreviation LG throughout this course for Lie groups and LA for LieAlgebra, for Lie algebras. And so when I read it, I'll talk about a Lie group, but when you see it printed, you'll just see LG and LA. Lie groups and Lie algebras as operators on a representation space. And we're going to use the abbreviation RS for representation space because we say it so frequently. We'll go over and over again talking about Lie algebras, Lie groups, and representation spaces. The elements of a Lie algebra, and by virtue of that, e to the lambda dot L, also elements of a Lie group, can be considered as operators on a linear vector space that supports their actions. In other words, we are imagining that this Lie algebra, being a set of operators by definition, by that we mean that they operate on something. And the thing that we want to let them operate on is a linear vector space that supports their actions. So for example, we write L times A is equal to B. This means we've got a vector in one space that's acted upon by an operator, and it changes it to another vector in that first space. Such a space as is represented by this ket vector is called a representation space, RS, for that Lie algebra, and also for the Lie group that would be generated. If and only if these actions, expressed as matrices, obey the commutation relations Li Lj is Cij k Lk, and the associated Jacobi identity. The basis of the representation space consists of those vectors which are simultaneously eigenvectors of a complete commuting set of operators formed from the L. Let me state that again. These vectors are going to be those vectors which are simultaneous eigenvectors of a complete set of commuting operators formed from the L. Now it can be shown that all of these commuting operators can be chosen as Hermitian and thus have real eigenvalues, and therefore the vectors are orthogonal. We will choose their lengths. We will choose their lengths to be unity. So let me state this once again, just for reviewing. We have a Lie algebra. It's a whole bunch of objects L. It's actually a linear vector space. They also have commutation rules with structure constants, as mentioned above. Those objects L will act upon another vector space and create from one vector another vector. They transform it. They may rotate it, translate it, multiply it by 6, do some other type of operation. The space on which we act is called the representation space of the Lie algebra. It supports that Lie algebra in a sense, and therefore it supports the Lie group. So what we're going to be doing is studying different Lie algebras and then trying to find the representation space that will support actions by those operators. In a certain sense, you could say the course begins with this next page. We're going to now talk about the Lie algebra and the representation space that supports it, and how we're going to take that Lie algebra and cast it into a particular form that's going to be of extraordinary use. The Lie algebras which we will use, primarily semi-simple Lie algebras as we find, will have elements, L mu, which can be chosen so that a maximum number of them, which we relabel as the HIs, all commute with one another. HI, HJ is equal to 0. Now what have we done here? We've said that out of all of the different L's that we have, we can find a set of those, a subset of the L's, and we're going to rename them as H's, such that in this subset every one of the elements commutes with every other one. A perfect example of that is like in quantum mechanics, momentum in the x direction commutes with momentum in the y direction, but would not commute with position in the y direction. The remaining L's can be chosen in particular pairs, which we're going to rename as E plus or minus alpha. In other words, they're going to be an even number that always remain, or a semi-simple Lie algebra, which we'll define later. And this is going to be so that the following equations hold. The H's, which is a maximum commuting set of these objects, commuted with the E plus or minus alpha, is equal to R sub I of plus or minus alpha, E plus or minus alpha. In other words, they take the form that H commuted with E gives us that E back again, times some vector summed over those. Secondly, the E alpha with the E minus alpha always gives us an H. Now, depending upon which alpha this is, that's a different vector, and this Ri is a summation over the HIs. And finally, the E alpha with the E beta commute so that we get a number in sub alpha beta, E alpha plus beta. And we'll explain this later on. We will also have relationships such that the R with the lower I of alpha is related to the R upper J of alpha by a structure called with the metric constant, with the a metric Gij, which can be found by contractions over the structure constants in the following way. The metric Gij is defined as C ILK C JLK, and we notice here that there's a contraction and summation over K and over L, leaving only I and J as free indices, and that this is always equal to the sum over I of Ri alpha, Rj alpha, and it's always equal to delta Ij. The HIs are a maximum commuting set and is called the Cartan subalgebra. The HI is the largest number, a maximum, set which commutes out of all of the L's, and therefore it's called the Cartan subalgebra. The E's, plus or minus alpha, turn out to raise and lower the eigenvalues that span the entire representation space. What eigenvalues? Eigenvalues of these various H's that all commute with one another. The selection of all of the H's and all of the E's is called the Cartan decomposition. Now, this page contains a tremendous amount of information, and let me just verbally go over it very quickly. What we've said is we start out with a bunch of L's, a basis for all of this linear vector space. It might be a 20-dimensional space, in which case there are 20 different L's, and mu would go from 1 to 20. We can choose among those L's linear combinations of them that are independent, which we define as the HIs, such that all of the H's commute with each other. That would leave, if we had, for example, I is equal to 1 to L, that would leave N minus L, which always is an even number. And we can choose the rest of the operators as linear combinations of those in pairs, E plus alpha and E minus alpha, so that the following commutation rules hold. The H's with the E's give us E's. The E's with a conjugate E gives us an H, and an E with another E gives us an E with the sum of the two values. The R with the lower I is related to the R with the upper I with a metric type of tensor, and this metric tensor is defined as a double contraction over indices between the structure constants. It's also equal to Ri Rj of alpha summed over or integrated over alpha, which is equal to delta Ij. Now this is really critical, and we'll see so much of the foundations of quantum mechanics when we look at this, because we will see that these maximum commuting sets are things that we can observe at the same time, and that the E's will turn out to be things that change those eigenvalues. They're called raising and lowering operators. Let's see if we can finish one more on the Lie algebra representation space. The number of basis elements in the Lie algebra is called the order of the algebra. That's how many basis elements we have, or the dimensionality of the linear vector space. The rank, R, of the Lie algebra is the number of maximum commuting elements. Therefore, R is always, this should be less than or equal to L. It would be equal to L only if all the elements of the algebra commuted with one another. Well, are there other operators which commute with all of the H's? Well, by definition, the H's are maximal, so they can't ever be another linear combination. That is, there's no way that we can take a linear combination of the E's that commutes with all of the H's. But we could have nonlinear functions of the L's that commute, and we could consider these nonlinear functions that obey this equation right here, so that these functions of L with L's all are zero. These are called Casimir operators, and they are nonlinear functions of the L's that commute with all of the L's in an algebra. They will certainly obey, then we can also consider nonlinear functions of the L's, which we call D's, that commute with all of the H's. They are like Casimir operators for a subalgebra. It follows then that all of the Casimir operators, since they're functions of the L's, commute with one another. It also follows that Casimir operators commute with all of the D-type operators. It also follows that the Casimir operators, by definition, commute with all of the L's. By definition, the D's commute with the H's, the D's must commute with the other D's, and the H's commute with the H's. Therefore, our fundamental result is we can label a vector with the simultaneous eigenvalues of all of the C-type Casimir operators, all the D-type Casimir operators of subgroups, and the maximal Cartan subalgebra, all of the H's. So when we list all of these elements, we have completely specified the representation space.